Lots of you may know that there are some theorems called no free lunch theorems. You think, oh, I have to do the introduction, trivial. Nope, not so trivial. Everybody has to get one of these pieces of paper. So, good morning. This talk is a talk about the interaction or interface between graph limit theory and statistics. So I have my statistics hat on today, and there are, of course, huge graphs, and it's exciting to see pictures of them and think about them. But it's important to remember that there are also many smaller graphs, and people are interested in them. People in sociology, economics, political science, biology often have to deal with collections of graphs which are 30 vertices or 1,000 vertices, that sort of thing. And also there's interest in how to think about them and how to work with them. And there's an enormous literature, applied literature, on network analysis. And one of the models or families of models that is proved to be useful are exponential random graph models. So exponential models. And one of the first ones, which is from the 1960s, but it's been developed a lot and used a lot, is called the Strauss model. And I'll just write it down. P sub beta of G, beta is a vector of parameters, is normal. Well, I'll write it this way. It's e to the 2 beta 1 times the number of edges in the graph plus 6 beta 2 times the number of triangles in the graph divided by n plus n squared times a normalizing constant. So this is a normalizing constant. This is the number of edges, and this is the number of triangles. If beta 2 is 0, then this is just the Erdős-Rényi model, written in a slightly unusual fashion. And people put in an extra parameter in order to try to deal with the fact that friends of friends are friends. So you would like mathematical models that allow you to have more triangles. And this is one way, natural way to do it. The scaling will become clear when we are a little more general, but if you just try this as a model for various natural choices of beta 2, you find that almost all graphs are empty, or almost all graphs are the complete graph, and somehow this is a natural scaling that works. Now, and of course people put in many other features of graphs, as I'll try to explain. Now, one of the problems is, okay, it's fine to write down such a model, but then you observe one graph, so problem. You observe G, and then you have to figure out what beta 1 and beta 2 are. Find beta 1 and beta 2, which are good candidates for the underlying parameters. You assume some model of this form holds. Here beta I are just in R. And one standard thing that people do is maximum likelihood, perhaps so you want to estimate, given 1G, you want to estimate beta 1 and beta 2, perhaps by arg max, finding the P sub beta of G. So you find the beta 1 and beta 2 with fixed G, which makes this as large as possible, and that's a guess at okay. There are problems with that. Applied people found problems with that, and problems. problem A is that the normalizing constant is unknown, and for many models unknowable, psi n unknown. And so it's hard to do the maximization when you don't know the normalizing constant. A second problem, which just came up in applied work, that model that I wrote up there is a very natural thing to do. Anybody might think about it, and many different people have. So it's not created as some math counterexample. And yet when people try it, they find that it's not well parameterized, so many different beta 1, beta 2 pairs lead to this approximately the same measure on graph space. Not exactly, but for many practical purposes. See another, so it's not practically well parameterized. Another problem is that you, for natural parameter choices, the following happens. You fix beta 1 and beta 2. You generate a graph, okay, with that beta 1 and beta 2 fixed. Then you estimate beta 1 and beta 2, and then you generate a second graph, and the second graph looks completely different than the first graph. So there's an instability, which it will come to explain. I'll call it the mixture problem. I'll explain that.
The number of edges and number of triangles are the same with other properties?
Yes, right. There'll be math coming, but this is what I'm going to try to talk about. And the final thing is, even though these really are natural models, there are phase transitions in them, so that tiny changes in beta 2 for fixed beta 1 in natural ranges, not extreme changes, lead to graphs which are almost empty or almost full. And so I'll put that as phase transitions. And so these are issues, and to be honest, I'm a mathematical statistician, and I find simple natural models of that sort, which are thought of and used by normal scientists, that show this kind of rich behavior, something worth thinking about. And that's what I'm doing here. It's not that I believe that this is a great model, but it's just they're natural things to write down. They're like many other things people do. And the fact that they have these kinds of problems is interesting to me. Now, of course, many of these problems are familiar in statistical mechanics and in other areas, but in statistics, these are new problems. The structure of the talk is, now that I have that up there, is I'm going to do two examples and say what kinds of things we find and can prove. Example one is the degree model. And that's work with Saurav Chatterjee and Alan Sly. And the second topic is these exponential, these Strauss-type models. But before doing that, I wanted to say an example of a scientific problem where all of this stuff is used, and it seemed like a reasonable thing to do to me. It's not my research, but I thought it would help to hear an example of who's doing this and what kinds of graphs are involved. The example has to do with models for studying flu epidemics in schools. So in a kind of high school or a school for kids, there are flu epidemics, and then there are questions about what to do. Should you have more injections? Should you close the school down? Those are problems that people actually have to face. And there are standard epidemic models. Standard epidemic model, one of the assumptions is random mating. So somebody in the school gets infected, and in this mathematical model, they infect a random other person, and those can infect other people. But there's a sort of random mating assumption, and then people run simulations if they can't prove theorems, and then they see what happens, how long the epidemic lasts, and how severe it is, and things like that. And a group of people have said, especially about something like flu, it's not random mating. It has to do with who knows who and how much time they spend talking to each other and things like that. And so they tried to make more serious models that incorporated that kind of structure. And the models, I'll give a reference, so this isn't something I can say very carefully, but I thought it was a good example of where people are using these kinds of models and techniques. So the modeling effort is in 3 stages. First, there's say there's a school of 1,000 kids, or n is some number, 1,000. There's a friendship model. And we'll take that to be an undirected graph from one of these kinds of models. I'll be more specific in a second. So there's a who knows who type model, who are friends. And then on top of that, there's a contact model. And of course, you have contact with your friends, but in a lunch line or in a classroom, you have contact with people who aren't your friends, and so there'll be less contact with non-friends and more contact with friends, that sort of thing. And then on top of that, there's an epidemic model, epidemic model. And so a way of thinking about it, there's a friendship graph of some sort, and then on top of that, imagine these lines and some gray lines for who has contact. And so there's a contact model, which these are stochastic models, and then somebody gets infected, and there's an epidemic model, which is if you've had contact with somebody for a certain period of time, there's some chance of transmitting things. And so this graph type model comes in as one part of a more elaborate modeling strategy, and then people run them on the computer and simulate various strategies to see how they do, how long does the epidemic last, how many people are infected, and that sort of thing, and how do different strategies impact things. As an example of the type of graph model that people use, I can put it here. A simple model might be that Pij, the ith and the jth person in the population, have a chance. So this will be simply an edge type model. It's e to the summation ai times, well, I don't know, I'll call this beta I. Times vi, no, not I, a, sorry, a equals 1 to k plus summation, I'll explain, beta a vj a plus summation beta ij, I don't know what to call it, vi times. Okay, let me explain. Each person has their boys and girls and in what grade they're in and how old they are, and actually race seemed to be a variable that was important. And it's divided by 1 plus the same. e to the same. So so these vectors v are covariate vectors. What grade you're in, your, say, race and your sex. This says that people with different grades could have different degrees of sociability. People of different races have different degrees of sociability, and girls and boys have different degrees of sociability. This is a set of parameters that are made up in order to say, well, you know, 6th graders are more likely to talk to 6th graders and less likely to talk to 9th graders, and black kids are more likely to talk to black kids and vice versa. So these parameters are fixed for the population, but these covariate vectors are you know, individual specific, and then you know about the composition of the school, and you make this modeling assumption, you fit these betas, and then they generate millions of graphs in order to do simulation. So it's just, I wanted to say an example of the kind of place where people are using graph models. If you wanted to look at this example, it's just appeared in the Annals of Applied Statistics. It's quite a readable paper, and the many details that I'm not going to be able to tell you. I hope I wrote down its reference. Yes, Potter et al. Estimating within school contact networks to understand influenza transmission. I'll abbreviate, flu, and it's in the Annals of Applied Statistics, 2012. And if you look, you'll see good pointers to a host of other literature. So there's lots of people doing things like that, and does the kind of thing that we think about help them, or can we tell them they're silly, and et cetera? That's a kind of question. Okay, so let me get to something that is more well-formed and also that I know about. This is other people's work. And so here's my first example of some math. Example 1, and this is the degree model, and so I'm going to put a probability distribution on graphs of with n vertices, where the model is p beta of g. The chance of seeing a graph is proportional to e to the sum of beta I di of g, I equals 1 to n, where di is the degree of vertex I. So these are labeled vertices. And so this is a model that has n parameters as opposed to that one which had 2 parameters. Okay, there are n parameters in this model. Okay, and I thought of this model in the following way, in a statistical mechanics way. People like Barabasi and others have been talking about power law type graphs and degree distributions as if that was an endpoint, and if in fact the degree distribution is all that matters, then this is the most random model with a given degree distribution. It's the exponential family through the degrees of sufficient statistics, and so it says that the degrees are all that matter. Anyway, it's a model, and it has been considered by lots of people. So the object is you observe one graph, boom, G, and then you want to estimate the n parameters. Okay. So, as an example of a kind of theorem that we can prove, and the asymptotics in this theorem are n is large, but it works fine when n is about 30 or more, and certainly works when n is 300,000, but it also works when n is 30. Generate G from this model store, 1G, and suppose I need to suppose something that beta I is bounded by something. There exists, this is universal, it doesn't depend on anything, it depends on L. There exists a constant C sub L such that the first thing is that with probability bigger than 1 minus C sub L over n squared, so with high probability, beta hat MLE, the maximum likelihood estimate of this vector of parameters exists. It doesn't, as I'll explain, it doesn't always have to exist. And the maximum deviation of in I of beta, I'll call it I hat MLE from beta I is less than or equal to some same constant, if you like, times square root of log n over n. And so all of your estimates of the parameters are close. Okay, so that says that from a sample of size 1, you can estimate n parameters. Okay, a little surprising, if you want to see an example, on the handout in the back, not with the colored pictures in the back, these are two pictures. This is taken from the paper with Sharif Chatterjee and Alan Sly. We just tried it out. We tried it out a lot. I'm not showing you a lot of tries. So this was with n 100. And so what we did is generate betas uniformly between -3 and 3, or between -1 and 1. Just generate 100 betas at random. Generate a graph with those betas, and then estimate the betas from the graph that you see. Just try it out. And this is a graph of the parameter values versus the estimates. And, you know, it's pretty good. You're estimating 100 parameters based on a sample of size 1. When n is 300, it gets better, and it gets better. You know, so you can actually do it, is the thing. Yeah?
Is there a smart way to generate these graphs?
Yes. Yes.
What was the question?
Is there a smart way to generate these graphs?
And does it have anything to do with the Poisson cloning model? Is it related? Or?
Not that I know of. These graphs, this is one way of saying the model. Another way of saying the model is the chance, it's a random edge model, is e to the beta I plus beta j over 1 plus e to the beta I plus beta j. That's very easy. You fix the betas. You just flip a coin on the ijth edge, generate. That's the same model. So it's easy to generate. Also, owning up, we both caught me. Because of this, we know this, and that helps a lot. So we know the normalizing constant. But still, okay, it's a model. It's an example. You can prove theorems. I want to make some remarks and relate it to some other parts of math, especially ones that are in this conference. Put that up. So what do I mean by the maximum likelihood estimator exists? So note, let me take n equals 2. Okay, that's the case. Either the graph that you generate is like that, an empty graph, or like that. The chance of the empty graph is 1 over 1 plus e to the beta I plus beta j. The chance of this graph is e to the beta I plus beta j, the same normalizing constant. Right? Just if the betas are fixed, this is the chance of generating the empty graph, this is the chance of generating that graph. If you want to maximize this, the biggest it can be is 1, and that is achieved when beta I and beta j are both minus infinity. Right? So beta I hat is minus infinity. Well, that's not a number. And here, the maximum is when beta i's are infinity. So that also isn't a number. So we say the maximum likelihood estimator doesn't exist in that case. Okay? There's no... So one part of the statement of the theorem is that with high probability, when n is large, the maximum likelihood estimator does exist. So in order to prove my theorem, I assume that beta is in a compact set. Right, but I'm just saying, if you have this model and you maximize it, you know, that's where the maximums occurs. Here's a problem. Which I can't solve, but which comes up in the proof of this. So I conjecture that the MLE for this degree model exists if and only if the observed degrees are contained in the interior of the Erdős-Galai polytope. I'll explain. So, as many people in this room know, but also many people don't know, not every sequence of degrees, purported degrees, can be the degree sequence of a graph. We say that a degree sequence is graphical, and I'll make, without loss, d1 bigger than or equal to d2 bigger than or equal to dn. Suppose you order them that way, it's called graphical if for every k, the sum, I equals 1 to k, the sum of the biggest k degrees is less than or equal to k times k minus 1 plus the sum from I equals k plus 1 up to n of the minimum of d I and k. This part of the bound is easy. It's easy to see that this inequality holds, and the other part it takes some doing. The set of all degree sequence is a famous object. It's convex hull. It's called, I don't know, the degree polytope or something like that. And we believe that the extreme points of this are given by threshold graph models. And so it's a very well studied polytope. And we believe that the MLE exists if and only if we're in the interior of that polytope. Haven't proved that. The reason I told it to you, well, first of all, there are a lot of smart people in the room, and maybe somebody will prove it. That would be good. It's probably true. But this kind of thing comes into the theorem, and you can't see that because I've said it as statistics, so I want to tell you a graph limit version of some of these things. So this theorem, which, as I said as a statistics estimation theorem, uses a lot of tools from graph limit theory, and here's one of them. So this is something from the middle of the paper, which I'm going to try to explain now. When does a sequence of degrees converge? Well, there's various a sequence of degree sequences converge. There are various notions, but I'm going to say di of n, sequence of degrees. These are graphical sequences, converges, and they're ordered to a function f of x on 0, 1. F of x is on 0, 1. If we need these conditions, these seem to be what we need, di, d, 1 over n minus f of 0 plus dn n minus f of 1 plus the sum from I equals 1 to n minus 1, I don't know, let's see, of d I n over n minus f of I over n goes to 0. So this is some kind of L1 convergence. So there's a limiting degree sequence, but we also seem to need for general, if f is continuous, we don't need these terms, but if for general limits, we seem to also need to tie it down at 0 and 1. So I'll say that a sequence of degree sequences converges if this tends to 0. Okay? The theorem that we proved, the main theorem of our paper, in fact, isn't a statistics theorem. It was looking at what a random graph with a given degree sequence looks like. Suppose din converges to a limit f. So suppose I have a sequence of degree sequences. So I have a large graph, and I'm doing this as asymptotics. Suppose that I have a sequence of degree sequences which converges to f, and choose gn with degree sequence din uniformly. So take a degree sequence, choose a random graph uniformly from the set of all graphs with that degree sequence, and what happens? So what does a typical graph with a given degree sequence look like? I think there are no more assumptions. Suppose that these converge, then there exists a unique g of x such that if you make the kernel wxy to be e to the g of x plus g of y over 1 plus e to the g of x plus g of y. So that's now that's a kernel. I'll try to be orderly. Put that there. Well, hope that's okay. So then this kernel has f as its purported degree distribution. There's a, okay. Then the integral of wxy dy is equal to f of x. That's what the degree distribution should be. This is from 0 to 1. Of course, there's an assumption. And Gn, my random graphs, converge. I don't know how to write it, so I'll write it this way, to W in the sense of graph limit theory. So a typical random graph with a given degree sequence looks like this kind of graph limit. There's an assumption in this theorem. This is if f is contained in the interior of f, and f is the set of all possible limits of degree sequences. The reason I wanted to tell you this theorem is that in the course of proving it, we needed a continuum version of Erdős-Galai, and that characterizes when something is in the interior of f. So a theorem along the way is that f is contained in the interior of the set of all possible limits of degree sequences in this sense, if and only if there exists C1 and C2, so that 0 less than 1, strict between 0 and 1, such that f of x is bigger than or equal to C1, less than or equal to C2. And the analog of the Erdős-Galai condition holds, namely the integral from 0 up to x of f of y dy is less than or equal to x squared plus the integral from x to 1 of the minimum of, where am I, x and f of x, y and f of y and f of y dy. So there is this continuum analog and of the Erdős-Galai theorem, and all of these pieces are important in working with these, in improving these statistics theorems. Second question. The first question is prove something about the MLE in the degree model. This was the natural version of the theorem characterizing the interior for our purposes. Probably this isn't the final version of the theorem. With somebody who likes things like that, and there are a lot of you in the audience, some in the first row, and maybe it's already been done, did you think about any other version of the Erdős-Galai theorem for graph limit space? That's a natural question, and we have one. This is all in print. This is in the Annals of Applied Probability last year, and you can look. So that's my first example. What I wanted to tell you about in this example is a summary of the first example. It's that natural statistical problems can lead to mathematics. You try to prove that what applied people do actually works, or try to break it and find that it doesn't work. That can lead to mathematics. The mathematics, it's hidden, you wouldn't have known it, but the mathematics that we found useful is part of graph limit theory. It really was a very useful language to describe things in. And sometimes coming into a problem from an applied area, as this one does, can lead you to new theorems in graph limit theory. So of course, that's the way it should be, but this is an example where that seems to have happened. Okay, so that's my first example. And there's many things I'm not telling you about this paper, but the other summary is that this idea of using the maximum likelihood estimator, even in this case, we can estimate n parameters based on a sample of size 1. Now, of course, that's cheating. We have n choose 2 edges, I understand. But I'm estimating n real numbers in a strong sense uniformly based on n choose 2 zeros and ones. It's kind of surprising to me that it worked. And it actually works. We also had a fast algorithm for computing the MLE and proved that the algorithm converges and many things I'm not telling you. Okay, so that's a little look at some mathematical statistics. So that's example. Okay. Now, to not get lost, I made a list of what I want to tell you, and I hope I didn't forget anything, but whether or not I did. Okay, so one might think from this description, gee, we can estimate many parameters just based on a sample of size 1, so 2 parameters should be trivial, okay? And so sometimes, and that was discovered by applied workers, low-dimensional models are not so trivial. I want to set this up in a way that makes some sense. So let me say a general version of an exponential model. So this is part 2, example 2. So low degree models. Output can be interesting. Okay, so in general, I don't know what we call it, so I'll just call it this for now. Let big script W, D box, be graph limit space, the set of all kernels with this wonderful box metric on it. That's graph limit space. And so this is all kernels. as a topological space. And suppose that I have T, a function from W into R, which is continuous, and you can get triangle counts and edge counts, as I'll remind you, but you can get degree distributions, linear combinations of degree distributions, and the eigenvalue distribution. There are lots of continuous functions from graph limit space. And then we'll, Gn is all, n vertices, all n-vertex graphs. My probability measure, Pn of G, is, well, what is it? It's T of G applied minus this normalizing constant. I'll call it psi n, saying nonsense. So there's an exponential factor that's missing, and let's put that in properly. It's e to the n squared times this graph parameter, or linear combination of graph parameters, minus, the way I write it, the normalizing constant. And psi n is just the normalizing constant. Psi n is 1 over n squared, but it's useful to write it this way. It's the log of the sum over all G in Gn of e to the n squared T of G. And so that's a typical exponential model. It includes lots of different things. I also need this piece of notation, the entropy notation. I of u, use a real number, is 1/2 u log u plus 1/2 1 minus u log 1 minus u, okay? And you extend that function to kernel space by I of w, if w is a kernel, is equal to the integral of I of w xy dx dy, 0, 1 squared. So that's a parameter that'll come up. And a first theorem in this work, this is with Sharaf Chatterjee, first theorem is that theorem 1 is that these normalizing constants have a limit. The limit of psi n equals, so this limit exists. It's just as numbers, and it has this description. It's this variational description, the sup over w of, I'll call it T of w minus I of w. So it has this variational characterization, and this hidden in this theorem is this marvelous large deviations result of Chatterjee and Varadon, and the compactness of graph limit space says that this exists, and therefore the regularity lemma. So simple as it is, this is it has a lot of machinery hidden in it. So using this, there's a law of large numbers. So theorem 2, and I'll call it a law of large numbers, which is let F be the set of all W such that the sup occurs. This sup occurs. That's a non-empty compact convex set, F is. And then for every challenge number eta greater than 0, there exists C and delta greater than 0, such that the probability in graph n space that the box distance between a random graph chosen from that model and this set F is bigger than eta is less than or equal to c times e to the minus n squared delta. And how explicit these are, well, they do become explicit when you get into doing examples, but if f, as will happen in a lot of cases, is 1 point, that says that most graphs are close to f in graph limit space. And so a typical pick from this measure concentrates around the limit, and anyway, it concentrates around the maximizers of, well, not so good. Okay, so as an example of that theorem applied to those examples in that corner, or let me extend a little bit. So theorem 3, I'll call it. Suppose that HI, or edges and triangles, some finite collection of graphs, they're fixed graphs, and take T of G, I'll do this in this language, is the sum, I equals 1 up to k, of some fixed parameters times the homomorphism density. So this is the proportion of homomorphisms of, the number of homomorphisms of Hi into G. And that can be rewritten as those models in those cases. And now here's an important thing. Say beta I is positive, bigger than or equal to 0, 2 less than or equal to I less than or equal to k. Beta 1, which is the edge density, I'm always going to take H1 to be K2, just an edge. Suppose that the beta i's are positive, then we can say what the limit is. The limit of psi n it's a one-dimensional maximization, max over of summation of beta I, u to the number of edges in Hi minus I of u. So this is a polynomial, I equals 1 to k. This is a polynomial in u. That's what the limiting object is, and this polynomial might take its values at several different points. So now, go back to these pictures. I'm sorry the Xeroxing a Xerox in color doesn't work great, but anyway, let me at least try to explain some of these pictures and explain what they have to do with B, C, and D over there. So I'm working in this example in the edge triangle model, that model and that parameterization, and those are beta 1 and beta 2. And so there is beta 1 and beta 2 are, well, here both positive and negative, but beta 1 is allowed to be negative, and beta 2 is like this. This is the maximizer. This is a picture of the surface of the maximizing u of beta 1, beta 2. And as you can see, it's smooth here, but it has kinks here. And I'm sorry, there's a much better picture, and certainly this is on both of our websites and on the archive and et cetera. This paper is on the archive. And so, but if you want to know what do these functions look like, this is a typical function. This function is a function of u in this edge triangle model, and their functions, and it's very easy to find the maximum. You just look at a picture of it if you like, but you can do it numerically as carefully as you like. And so you've gotten down from this infinite dimensional maximization problem, that one up there, to a one-dimensional problem, and that's an easy thing to do. So let me look at some of these points. Well, first of all, psi n is unknown. What we propose is to use this as an approximation to psi n. It's a function of the betas, and then you can optimize it. And that works well, comparison with anything else, but by serious comparison, it works well when n is 30. I mean, it really seems to work very well. So that's a step forward, using this as an approximation to the normalizing constant. That's point A. Point B, many different betas give the same, oh, I should have said that. And Gn is close to, in the sense of graph limit theory, is essentially, is, in the sense of limit theory, an Erdős-Rényi graph with the maximizing U star. So that the limit is, and of course if there are several maximizers, then it'll be a mixture of some of those. So, sorry, a typical graph taken from this edge triangle model looks like an Erdős-Rényi graph with parameter given by this optimum. And that theorem, I should give credit to Bahamati and Sly, who proved it in useful special cases, and then we proved it in some kind of generality. This picture is, here's beta 1, here's beta 2. These lines are beta 1, beta 2 pairs where the maximizing U star is the same. And you can tell this region has lots of, so there's a lot of essential non-uniqueness. Now, these are limiting theorems, but in practice, people noticed that it was very hard to identify beta 1 and beta 2, and this proves that in some sense. The idea about mixtures is, you can see from this set of pictures here, this is this plot. It's the same edge triangle model. When beta 1 is fixed at minus 0.8, and then it's as a function of beta, so there's U, and then for different beta 2 values. And what you can see is that this function, well, here it has a maximum here, but that maximum is perking up, and there definitely is a place, you can figure out where it is numerically, we do it in the paper, where the maximum is taken on twice. And that was found empirically by Mark Hancock and his group. That is, so what would it say? There are two different maximizing U stars. That means, and here it turned out to be half the time one and half the time another. So they're very different Erdős-Rényi graphs. This is a final answer to your question. They're very different Erdős-Rényi graphs. They have different densities. But if you generate half the time you'll get one and half the time you'll get another. Now, of course, you're generating from the edge triangle model as far as you're concerned, but still, something very disquieting goes on. You generate graphs from the same model, and you get very different looking pictures, and sort of constant valued pictures. And the final point about phase transitions, if you turn to the other page, this is a plot of U star, the maximizing Erdős-Rényi value, it says here, on the y-axis, how high it is, versus beta 2 on the x-axis for 4 different values of beta 1. And now, so, these are honest phase transitions. These are honest discontinuities in a partition function, in limiting partition function. So here, when beta 1 was, minus 0.45, there really is a jump. And when beta 1 is minus 0.8, for tiny little changes in beta 2, the graph is almost empty or the graph is almost full. So there really are some changes. This was observed by empirical workers, and we're able to prove it in this set of cases. Okay, so the summary, as it were, because time is more or less over, the thinking about bread and butter statistics problems, estimating parameters in this edge triangle model is a classical statistical problem, led to some hard, honest work, and it used graph limit theory and much of the machinery that's being developed by people in this room in a really non-trivial way, so I'm very thankful that you've been making available and making it available. So that's my 2 examples. Thank you. Good.